So in this session, we'll be studying two different types of controllers. One is a sliding mode controller, and the second one is a predictive controller. So far, we have studied the PID-based controllers, the P, PI, PD, the integral, derivative, and proportional controllers. We have studied the fuzzy logic-based controllers. We have studied the neural network-based controllers, how fuzzy logic works, how neural network works. In a similar fashion, we'll study the overview of a sliding mode controller and a predictive controller, just giving the outline, a brief outline of the operation of these controllers. So, firstly, let's see the sliding mode controller, or what's also known as SMC. So, what an SMC does here is, let me take an example of a system whose transfer function is 1 by s minus 2. We understand the total transfer function of this system will be 1 by s minus 2 divided by 1 plus 1 by s minus 2. That's 1 divided by s minus 1. So one of the poles of this total transfer function is still located in the right half of the S-plane, and so, as such the system is unstable. The system by itself, 1 by s minus 2, has an open loop pole at s equal to 2, so it's unstable. Even if we use a unity feedback system without making any change, the system still remains unstable. Now, what we can do is we can use two different gain values, plus 1 and minus 1 here, to uh, switch, obviously. So at one time we'll be using a gain value of plus 1, at another time we'll be using a gain value of minus 1. What this plus 1 and minus 1 here actually suggests here is that if we are using plus 1, we'll be having a negative feedback system. That's what mostly is used. But if we use minus 1 as the gain value, the overall system will be having a positive unity feedback. That such systems are actually not preferred. Now, if we are, say, for example, first using a gain value of plus 1, we'll get the total transfer function will be this 1 by s minus 1. So the system is still unstable. There is no doubt about it. So if we say this is the stability value, the system will rise and it will keep on rising for the value 1 by s minus 1. This is just an illustration here how the system is behaving. The system will be exponentially rising, and it will not settle at the steady state value if we are feeding a step input to the system. Right? Now, if we are taking this is at plus 1. Now, if we take the minus 1 value, that is, this plus 1 actually means the negative feedback loop. Now, if we take minus 1, our total transfer function will be 1 by s minus 2 divided by 1 minus 1 by s minus 2. That actually corresponds to an equation of positive feedback loop, that is 1 minus 1 by s minus 3. So this is a positive feedback at this time. So what we have done is we have simply switched between a positive feedback and a negative feedback. In both cases, the system is unstable. For this, the pole is at 1. The system is unstable. For this case, the pole is at plus 3. The system is still unstable. Now, the only difference here is that we have a negative value. That means instead of Say, for example, the system rising like this, it will be falling like this in this direction. So the effect is that with a positive feedback, with a negative feedback, we'll have a rising unstable curve. With a positive feedback, we'll have a falling unstable curve. So if we now actually make an algorithm such that we switch it between positive and negative feedback. So initially let it be running at negative feedback, and then at this point we switch it to positive feedback, so it will start falling. Now we again switch it back to negative feedback, it will rise again. In all the cases, the system response is unstable, but we are making it switch between positive feedback and negative feedback. So with the positive feedback, there will be a negative unstable curve. With a negative feedback, there will be a positive unstable curve. And now with this switching between positive and negative feedback, we are actually getting a response like this. We'll make an algorithm such that this system starts tracking the steady state value, starts sliding over the steady state value. That's why the name sliding mode controller. The system is not actually, it will never settle at the steady state value, but because of the switching algorithm that we are using, we are switching between a positive feedback and a negative feedback. We are making the system response to slide over the steady state value. It's constantly switching over along the steady state curve, steady state axis. So we can say the system now becomes, uh, if not, we cannot say with definitely stable. It is not a stable system. The overall system response is still, there is still instability in this system, but the characteristics of this system has now switched from instability to partial stability. We have made this, and if this switching is done at even a much quicker pace, you say for example we make it switch like this, the quicker the switching of positive feedback and negative between positive feedback and negative feedback, the more the accurateness of the better will be the accuracy of this system, and it will start tracking this steady state value. So sliding mode controller simply it's a switching algorithm wherein we make the system uh, switch between a positive feedback and a negative feedback, we can say that. And because of this switching algorithm, the output response is not exactly following the steady state value, but it is sliding over the steady state value. It is switching actually across this steady state value. So without going much into the details about sliding mode controller, we get this that sliding mode controller simply uses a switching algorithm. Uh, it uses a number of algorithms. Switching algorithm is one such basis of sliding mode controller. Uh, Using this algorithm, we can make the output follow the reference by making it slide over the steady state value. We have to actually define the sliding surface here. We have to define the equations for the reference trajectory. Then how actually a sliding mode controller is implemented. This is a basic form of sliding mode controller. Uh, there, there's more to it, but for now, this should suffice us in this semester. Uh, Secondly, we'll be studying a predictive controller. The most commonly used predictive controller is a model predictive controller. So a model predictive controller will use the model of the plant. So if we are, say, for example, controlling a DC motor, we'll be using a state space model of a DC motor, and using that state space model, we'll be able to the control the states of the system of the DC motor of any system, whatever we are actually trying to control here. So there are a number of inputs to a model predictive control. One will definitely be a reference value. We can uh, feed the information about the disturbances. We can feed the constraints. And accordingly, the model predictive controller will decide the manipulated variable that goes into the plant, into the uh, if we are trying to control the speed of a DC motor, the manipulated variable will feed the information necessary for control of the speed of the DC motor. Now this plant will also consist of the driver circuit and extra all those things. So what does a model predictive controller do is it uses the model of the very plant that it has to control, and using that model it predicts the future value of the manipulated variable, keeping in mind the reference values, the disturbances, and the constraints on the system. With keeping all these inputs into mind, using the model of the plant, it will be able to predict the value of the manipulated variable. That will help us control the output of this system. So what a predictive controller does, it will predict the future behavior of the process under control. Uh, uh, it, it derives the best possible value of the manipulated variable feeding the system. What we'll be doing here is that we'll be comparing the actual states of the system with the desired values, and based upon some optimization algorithm, an optimal value of the manipulated variable will be derived. So this value will be a predicted value based upon the model of the system. Fine. So this model predictive control actually optimizes an optimization algorithm. We have an optimization algorithm that will define the characteristics of this controller, and we will be trying to optimize the value of that algorithm, find the optimum value of the manipulated variable using that optimization algorithm. Uh, so we have already a past value of the systems, we have a reference value of the systems, and using that knowledge about the system's past values, about the reference values, we'll be able to, and using that optimization algorithm, we can predict the manipulated variable feeding the system. Another thing here is that it also takes into consideration the disturbances feeding the system. That way it helps control the disturbances in the system. If there is any external disturbance feeding this plant, be it a measurement disturbance, be it a white noise, a Gaussian noise, all those disturbance values, we can also model them and feed the predictive controller the knowledge about those disturbances as well. And one more thing is we can also constrain the output, constrain the values of the manipulated variable to a certain degree. Say, for example, we are controlling the speed of induction motor. Uh, the quicker the response of the system, that also means the current in the system will be very large at some point of time before it reaches a steady state value. So if the transient is very quick, if the speed response is very quick, that also means there will be a very high current value that can actually be dangerous for the system. So we actually even feed this information to the predictive controller, to this more MPC, way that we need to constrain the values of this armature current between these values. Say for example, plus minus 10 amperes. We'll feed this information. So within those constraints, it will try to predict the value of this manipulated variable such that it is able to control the output of the system in the least possible duration of time. Uh, so this model predictive controller actually, for this we need to understand somewhat the optimization theory, how we actually optimize, how we actually minimize the cost functions, minimize the value of these optimization algorithms to predict the best possible value of the manipulated variable. So that's something that we that we studying in higher classes in master's degree probably. Uh, so this is just an overview about a sliding mode controller and a predictive controller. These are very advanced control strategies. There's a lot of mathematics going behind in the sliding mode controller, the predictive controller. Besides this, there are some other control schemes like the H2 controller, the H infinity controller. There are a number of controllers that available in the literature that have been studied that can be used for optimization, for control, for estimation purposes. Uh, at some point of some stage, you'll have to go through these control algorithms, go through these optimization algorithms. So this is all about the sliding mode controller and a predictive controller. Just the overview about sliding mode controller and an predictive controller. With this, we actually wrap up this course.